So the premise of AI is actually that we've been building AI models for several years, actually, at InfoSupport. And I believe it's been 9 years now that we've been doing this. And the interesting thing is, at first, when I started building machine learning models, I was all like, oh, it's working. Metrics are perfect, 96%, 97% accuracy, all the best. Great stuff, actually, if you're just starting out. And I do feel that's a great first step. But there's a problem with that yes, it works, but do you know why it works? It might work for the wrong reasons. It might actually not work at all in the end if you start producing predictions on production. So today I want to talk about not trusting your models, but explaining them to make sure that they are predicting stuff for the right reasons, rather than just doing something random. I work as a technology advocate for InfoSupport and an AI architect. So my daily job is to build machine learning models. If you're interested in more, you can also follow me on Twitter if you like. So today we're going to cover why should you actually explain a machine learning model. I mean, there must be a reason, and we're going to explain a couple of things around that. Then we'll start pulling apart a black box model that I trained for this purpose. So I'm not going to explain how to train a machine learning model. That's a different talk. There are many talks today and yesterday that you can watch back on YouTube about this topic. I'm going to skip over that really quickly. And we're going to pull apart the black box and take a look on the inside. What's actually important to a model? How do I discover what's going on? Then the next step is we're going to debug the model, actually. So the first step is to get a structure. And then the next step is to take a look at specific predictions that we're making with the model and discovering, are these predictions made for the right reasons? And that's an important question to ask yourself. And what can I do if it doesn't work? We can actually show you that. And the last thing is, you can use this technology not just for structural discovery, debugging purposes, or just general interest. You can use this for your customers as well in production. And this turns out to be a very important scenario. So that's what I want to cover today as well. So let's first talk about why should we actually explain a machine learning model in the first place. The thing is that people are getting educated about AI. And the first level of education that they got about AI is actually AI is bad, killer robots, it's really dangerous to have automated decisions in your life. But quickly we discover as a society that we've been using AI far longer than we actually realized, maybe. Things like TikTok, things like Snapchat, Facebook, WhatsApp, Outlook, name all the applications that you're using in your daily life, and there's an AI component in there. So the next level of education is actually, okay, it's nice that we can use AI for several tasks, but I don't trust my model, actually. I want to make sure that if I am denied a loan at a bank, for example, that I get an explanation, even though the bank is using machine learning. That's a reasonable request to ask. So one of the best quotes that I found is actually from Gartner in this regard, is that new approaches to building interpretable systems and operationalizing AI models is important, is imperative actually to the success of AI. So it's not just about building a model and putting it in production somehow, maybe emailing it to the ops guy and he or she will put it in production. It's also about being able to supply information to your customers about the performance of the model and actually explaining why the model works, and adding information about when it doesn't work and what the customer can do about that. For me personally, there are 3 things that are very important when we talk about explaining a model. And these are 3 reasons why I think you should be able to explain your model. The first one is robustness. If you train a machine learning model, you often use metrics to check if your model is doing the right thing. We've all used precision, recall, accuracy. We've actually looked at the error margin in regression models. We maybe check manually what a recommendation system is doing. But those are pretty high-level metrics to explain how good a model is doing. It doesn't give you the level of detail that you might need to be really sure that a model does work in all different cases that it might encounter in production. For example, overall, your model could be having an accuracy rating of 97%, but it might be actually doing very badly for one of the categories of users that's using your model. It might well be that old people are getting a bad answer because they happen to be a different sort of data sample than younger people. It could be, and in those cases, you could quite ask yourself, is it fair even? But yeah, robustness is one of the reasons why I think explainers are a good thing to have, because now you can dive into more details how your model is doing for different groups of people, different sorts of samples in the data set that you use for training. The second reason why I think explainers are important is that these days, because people are getting more educated about the use of AI, they start to distrust AI, and that's a healthy distrust. I think it's very important to distrust an AI model because it makes mistakes. So there must be some way to check that the model made a prediction for the right reason, and that people are watching the model, that it doesn't do things on its own that it's not supposed to do. So that's the second reason. And the third reason is fairness. These days, there's a lot of discussions. We've all been there with Black Lives Matters, the whole discussion on Twitter about male versus female people in our IT population, or any other gender identification that you might have. I think a model should treat everyone equally, and in this case, we're talking about equal opportunity. That's one of the key things. There's more to it. I'm not going to dive into great detail about fairness. Actually, we're not covering it at all today, but there's a great presentation on YouTube in the global AI community about Fair Learn that explains more about this topic. So now that we know why you would actually use an explainer, then the next question is, how am I going to pull open the black box, that's a machine learning model, and take a look inside and discover why is it showing certain behavior? Well, there's two ways in which you can look at this problem. The first way is looking at model level explanations. And the second one is looking at prediction level explanations. The first one, the model level explanation, shows you the structure of the model, and it explains what happens on average. That's still high level. There is no such thing as an average sample. You might get lucky, but I don't think there is one in a usual machine learning scenario. So that's important to keep in mind, that the model level explanations show you the structure of the model rather than what's happening on a prediction per prediction basis. Roughly speaking, a model level explanation gives you information about the impact of certain features on the outcome of your model. So what's the impact of age on the outcome of a model? What's the impact of payment history on the outcome of a model? Maybe skin color, maybe pixels in a picture, those kind of things. If you want to dive into more details, if you want to look at a single sample, so for example, a customer comes up to you, has used your machine learning model, and the model made a mistake, then it's useful to look at a prediction level explanation and see why is it failing? And what do I need to do to the sample to make it work actually in the model? So that's what we're going to talk about today for half of this session. And it's really useful. These are really useful tools. I have to say it's a pretty new field, so there's a lot of research still happening. My demo code is on GitHub, so you can actually read the papers that are associated with my talk and my demos that I'm going to show today. Feel free to take a look at that if you're interested in more details. Okay, so let's start by pulling apart the black box model. And in this case, we're going to take a look at a credit card defaulters data set from UCI. It's a Berkeley University that provides a great set of machine learning data sets that you can build models on. And one of the things that I did is I built a model for credit card defaulters. Basically, what happens is I have a bunch of information about users, about customers, about their payment history, how much were they billed for their credit card, how much did they actually pay, and how fast did they pay for that. Alongside of that, there's some demographic information, such as age, gender, marital stage, and education level. And these are more sensitive things, but still, yeah, it's an anonymous data set, so we can actually train a model on that. And I trained a model, a random forest classifier. So it's a decision tree, but rather than one, there's 100 of them. And together they decide whether somebody is going to default on their credit card payment or not. So that's what we're going to talk about today. And before we dive actually into code, I can show a little bit about the training logic that I use. Let me first explain what we're going to take a look at. One of the first things that's interesting about a model is, of course, the performance itself. I'm not going to show that today. That's really the accuracy and precision stuff that I just explained. We're going to take a look at feature importance. There's a specific technique that you can use, feature permutation feature importance, it's called. And basically what it gives you a chart that looks like the one you see on my slide. In this case, it shows 5 features in total. And the top one is the most important one, and it then gets gradually less important down the line to the bottom. I limited it to 5 because that fits on the slide and makes the most sense. What I can see here is that my pay_1 variable is actually the most important one. How should you read this actually? Basically, what permutation feature importance is doing, it's going to grab one feature in your data set, and it's going to shuffle that feature, and then train the model as before and gauge the, well, it's not going to train the model. It's actually making predictions using the permutated data set, and then it's going to measure the performance of the model. And so if I were to change the pay1 feature in my data set and score the model, it would mean that my model is increasing in performance when I do that. In this case, I'm getting a 0.064% extra accuracy for my model on top of what's doing normally. If I do the same thing for pay_2 feature, I'm going to shuffle that one around and then score the model again. It only does 0.016% better than the original model. So that's how you interpret this. Let's take a look at some code and see how this actually works in practice in Python. So what I have is, and this is available on GitHub. So I have it on my GitHub account, github.com/my username/explainable.ai. We can post a URL in the chat, I think. You can take a look at that. You can download the code and give it a shot for yourself. So that's a useful thing to have. I have it here loaded up in Visual Studio Code, ready to go. So let me first take a little bit of time and explain how I actually trained the model, so you have a sort of a feeling in what direction I am going. What I did is I read in the training data, and I split out the label column into a separate variable. So the X variable contains all the features except the label column, because that's the outcome of my model. Then I have a second variable Y, which is the outcome of my model. So this could be a defaulter or not a defaulter in a separate variable again. And then what I do is I use scikit-learn to train my model. So I have a random forest classifier, and I can say, well, give me, using cross-validation, train my model, use 5 passes, and return the best estimator. So in this case, it's going to train 5 times, and with random sorting of the samples, and then I get back the best model that I can possibly get out of the data set. So that's the model. The data set that we're going to use, because that's important to take a look at, it's actually a CSV file containing all the features. So these are all the features. These are not really important. I will light up the features that are important in the explainers, but just so you know what's in there. So there's a bunch of variables for categorical stuff, for numeric stuff. That's all in there. Okay, let's take a look what we have. I know this model has a performance of 81% accuracy. So believe me, that's just the way it is. And it's not really good. It's not really bad. But let's take a look at what happens. So what I can do here is I can actually load up the model first. I've saved it using joblib, so I can load it up. I'm loading up my test dataset. This one is actually containing a subset of samples from the original dataset that I used for training and validation. And then what we have to do is we actually have to build an explainer. I'm using a library called Delex, and Delex is developed by the University of Warsaw in Poland. And they provide a very comprehensive interface for explaining AI models. And the way you use it is you import the Daleks library. You can install that on your machine, and then you create a new explainer. So let's do that and take a look. What it does, it reads in the data set, the test data set. It creates a target variable. In this case, that's the parameter y. And it tells me there's 385 values in my sample set. That's not a whole lot, but that's more than enough for the explainer to explain what's going on. At the end, it says, hey, I have a new explainer. Awesome. Let's see what it does. So you saw in my slide deck that I used the variable importance plot. Basically, what the explainer has a bunch of methods on it to either explain parts of the model, parts of the prediction, or make a profile of the model or a prediction. So that's pretty cool. It's all very consistent if you start using this stuff. So what I can do is, and this will take a second to load up. Basically, this generates the same plot as before, but it will do the permutation of my features and then plot the chart given the results. So in this case, I can see my pay1 variable is the most important one in my model by far. What does this tell me, actually? What can you derive from this? So the pay1 variable in this model actually has a value of -1 if somebody paid on time. It has a value of 0 or higher if somebody was late with their payment. So, for example, if somebody is 2 months late, it's very likely that that person is going to be a defaulter. And that makes sense if you think about it. I personally feel that people are very likely to be classified as a defaulter manually based on this first month, because once you're behind, and pay2 will also have a higher value, and pay3, which is also in this explanation, also has a higher value, because pay1 tells you about the payment status of the first month, and the pay2 about the second month, and pay3 about the third month. So if you're 1 month behind, the other ones start counting as well. That's what this explanation is actually showing us. And the other thing that's important is that luckily, my model behaves in such a way that it looks at payment history rather than gender, marital status, or education, which is a good thing. I think a defaulter model of this for this scenario, we should only be looking at payment history, not at age or gender. That doesn't make sense at all. You might actually question why a data scientist would put those variables in if we're looking at such a model. So that's good news actually for us. And as you can see, this is not really hard to do in Daleks. It's just a couple of lines of code, and you need to have some data ready to go for that. But usually you will have that if you're building a machine learning model. Now let's take a look at this next step. So we've discovered that the pay1 variable is pretty important to our model. But how important is it actually? That's the big question here. I can sort of see by the performance difference that I get in the previous chart, and this one, that there's a somewhat significant change in performance. It's not a huge amount, but yeah, let's zoom anyway. And this second explainer that we're going to use is an accumulated local effect chart. Basically what happens is the computer is going to change the values of one feature at a time, and then make a new prediction and check what the outcome of the model is. So in this chart, you can see on the left, I've got age on the x-axis, and on the y-axis, I've got the prediction of the model. So the higher it is, the more likely it is that the person is a defaulter. So 1.0 is somewhere here outside of the frame, and 0 means no defaulter. Looking at the age, I can see that somebody with the age of 30 is less likely to be a defaulter than somebody above 60. But the impact is very, very small. However, when I look at the second chart and I change the payment status of a person in this first month, then you can see as soon, so this one's actually on time, maybe a bit early even. This one's still on time. And then as soon as somebody gets behind on his or her payment, it shoots up. It's more likely to become a defaulter. So I can see from this chart alone that when somebody starts getting behind in the first month, that it's very likely that the person will be a defaulter. So the way you can do this in Daleks actually is that you can use a different sort of explainer for that. So instead of the model parts method that we've been using up here, we're going to use the model profile method. And I give it a type, so there's different ways in which you can profile the model and look at the impact of values for different variables. This one is the accumulated local effect, because that's the one that's makes the most sense in the case of a decision tree. So what I can do here is I can say, give me a accumulated local effect plot and plot it for the variable pay1. And what you will end up with is this chart. So you can see as soon as somebody is behind, it's all over. They are pretty much done for and classified as a defaulter. In this case, it only goes up to 0.6. So you have to keep in mind that this is just one variable we're looking at. And usually it's a combination of variables that determines the outcome in the machine learning model. So this is not entirely accurate. There's a small margin of error that you have to keep in mind. But overall, this gives you a pretty good sense of what the model is actually finding important. You could even argue here that I can train this model just on the payment status of the first 3 months, and the rest doesn't matter anymore. Because once you start getting behind, you're likely to be a defaulter. And it might be that the other variables are not that important. Even the bill amount doesn't make a lot of difference in this case, I think. So this is actually a pretty powerful tool. This already tells me a lot about my model, that I should be aware of the fact that, yes, I'm including 6 months of payment history, but yeah, only the first one is really important, and then it gets worse as we go along. So the model structure can be uncovered by first looking at feature importance, and then if you want to zoom in, you can use the model profile method and look at the accumulated local effects for more information. What happens if I change the value of, for example, the payment status in the first month? The second step is debugging your model, because the model structure only tells you on a very high level what your model is doing. It doesn't zoom in on any details. And as bad as this sounds, the devil is in the details in this case. It could very well be that in some cases we do look at age and other demographic properties. So let's take a look at that and see what it looks like. One of the cool things that you can do actually is you can ask your model to tell you precisely how it came to a certain decision. And this is called a breakdown method. And basically what this does, it actually takes all the features starting from the top. So this is the intercept. I'll get back to that in a second, but let's look at the first feature. So it will take the first feature and it will see what sort of output will that produce. So first it starts at 0.2. It starts to move to the right, closer to 0.3 or 0.26 it is. The second feature moves it even further into the area of becoming a defaulter. And the fourth feature in this case, bill amount 3, does the same thing. But then what happens is we move back slightly to the left. So basically what this does, it takes each feature on its own and starts bringing them together and say, okay, this feature adds to a positive decision. This other feature makes it even more positive. And then the next feature makes it even more positive. But in the end, when we look at all the other factors in the bottom, it decides it's not a defaulter because other factors have played a role in this. So this is a really useful tool. If you know that you have a prediction that's actually wrong for some reason, you can pull it through this breakdown explainer and take a look and see what it does. And most likely what you will end up finding is that maybe one of the values for the features was wrong. They made a data error for some reason. It could also be that the model is actually doing something really silly and you have to retrain the model with better data. That could also be the case in this scenario. But this is really nice view of your model from a prediction level. And the way this works in Delex is, if I pull open my other notebook that I have, is that I can use the same explainer. In this case, I have to load it again, but let's do that. I can use the same explainer class from Delex and say, I don't want to look at the model parts, but at the prediction part. So predict underscore parts. Let me actually zoom a bit in. Should make it bigger, smaller. So in this case, I can say predict parts, give me one of the predictions, one of the samples from my data set. I'm using the first row, and give me the breakdown, including interactions. You can also do a breakdown without interactions, and I will explain in a second what that means, but there's a big difference between the two, that's for sure. And then call plot. So I end up with the plot that we just saw. This is for a different sample, but it does the same thing. So it starts as an intercept, the sort of the base value, if you did nothing, and then start adding all the features together to come to a conclusion. And in this case, it says it's not a defaulter. The thing is, if you have a model that has a lot of interactions between different features, this will work, the breakdown with interactions. If you would use just the breakdown, it would make an unlikely explanation. So that's a word of warning from my side. If you start using explainers, it's also important to look at your data set yourself and figure out what does the data set look like. So people who have some experience with machine learning, as we know, a regression model, a logistic regression model, and a linear regression model for the same purpose has the assumption that the input features don't correlate with each other. They only correlate with the output. But in the case of this credit card sample, they do correlate amongst themselves. I mean, if we talk about payment status, if you're behind in the first month, you're behind in the second month. That's for sure. So that correlates. The bill amount in the first month will correlate with the bill amount in the second month. That's just what happens. There's a payment over time system actually going on. So in that case, if you know this information, you can make an informed decision about the type of explainer you want to use. And in this case, I would suggest you take a look at breakdown with interactions. That accounts for the fact that bill amounts and payment status columns will interact with each other and fix that problem. So this explanation is actually pretty sensible in that case. So going back to my slides, this is all pretty cool that you can do that, but it doesn't tell you the full story, actually. It only tells you, okay, this is how I came to the decision. So it's still useful, but it's important to take another look and take a look at what-if scenarios, actually. So it's nice that I know that the computer made a prediction, good or bad, based on my information, but I want to know what I need to change in order to change the outcome of the model. And in that case, we're going back to our profiling feature that Delex offers. And what we can do is actually say, on a prediction level, tell me what's the impact of a feature value on the outcome. So these charts look rather familiar if you've looked at the model structure. On the x-axis, we have, in this case for age, we have the age of the person. And on the y-axis, we have the outcome of the model. And here in the middle, there's a blue dot saying, this is the value for this prediction. So in this case, if I wanted to change the outcome of the model, I could try and change the age of the person. Maybe there's a mistake in there. Actually, as they become older, it becomes more problematic to pay back the credit card, apparently, but not by much. So this is a reasonably flat line. I don't think this has much impact on the model. Remember, at first, when we looked at the model structure, we discovered that the payment status for the first month was actually the one that's the most important to the model. So when you start looking at the prediction level, sometimes this might change a little bit, but don't expect much difference for the age column if that wasn't imported in the first explainer. So it's really narrowing it down in this case. So I'm going to look at the payment status for the first month. And in this case, I know that this person was on time. And that's likely the reason why they're not the default. But if I were to change it, saying, okay, this is behind, then it shoots up to 0.6. So this actually underwrites the same conclusion that I came to in my previous explainer, the model level explainer. A word of warning, it might actually be the same between the model profile and the prediction profile in this case, but it could be different for a number of reasons that we don't know exactly on top of our head, I would say, as data scientists. But it's worthwhile to take a look at that, because these explanations give you at least a hint of what's going on and what you might need to change. So let's take a look at what that looks like in code. As you've guessed, probably by now, I can use the explainer object again, and I can say predict profile. So in the previous notebook, we had model profile. Now we're going to take a look at predict profile. We're going to feed it a sample, the same sample as before, is this one that we used for the breakdown. And we're going to plot it again for the payment status of the first month. And what you will see is a familiar plot from the from my slides. Yes, this person is paying on time. Actually, it's -1, I think. Pay 1, I don't see it here in the list, but it's -1 at least. If I were to change this, moving to the right, so increasing the value, then the output would shoot up. Notice that this is not as much as the one that we used in the previous notebook. The previous one had 0.6. This one only has 0.30 something. Cool. So that's a really useful set of tools. What is important to keep in mind is that you use the right explainer for the job. So I can highly recommend reading the documentation of Delex and also reading the papers that I've linked to in my notebooks. These give you more background and a better understanding of what these explainers are actually doing. It can be important, especially if you have a weird bug. Then choosing the right explainer can make a world of difference if you're going to find a solution for that problem or not. So it's cool to see that explainers work in a debug situation. I can do this inside my Visual Studio Code environment. I can even go so far as push this library up to Azure and use it in Azure Machine Learning Service, although you won't be able to actually plot the explainers in the new explainer feature inside the Machine Learning portal. Currently, Azure Machine Learning Service only supports interpret-ML-based explainers. But then again, if you save the PNG files, you can look them up and take a look at that. And otherwise, I recommend checking out interpret-ML and seeing if you can find the same explainers in there. It's just that Delex has a much nicer interface for me, and that's the only reason I'm using it. Interpret-ML is pretty new. It's from last year, so they're still working on building stuff around that. Okay, so up until now, we've just used it inside our development environment and maybe test environments. But what about production? This information is pretty useful to customers too. And maybe you want to monitor the explainers on production just to be sure that the model doesn't start misbehaving for some weird reason. I mean, in production, we can already monitor for accuracy and precision and regression error margin. But an explainer would be actually a lot better, if you ask me. Not to say that you can't use the other figures, but explainers are useful in production. So one of the ways that you can actually use an explainer in production is by doing the following. So typically what you have in your solution is you have a piece of application logic that's gathering data from the user. This might be a microservice. This could be a web application. It could be a mobile application for that matter. And that application then sends that data somehow encoded to your machine learning model. And hopefully you've used ML ops such as Azure Machine Learning Service to deploy your model to production. And what you can do inside that model is, of course, you make a prediction towards the user, so they have their answer. But at the same time, you can queue the same data to an explainer service. So you can use Delex not just inside Python notebooks. You can also wrap it in a microservice and use it as a monitoring tool. And the reason why I have it here with a queue in the middle is that model explainers right now are not very scalable, sadly. If you look at a well-known explainer that maybe somebody has used already, the SHAP explainer, that one, if you give it more than 10 examples, then it will start crunching, and it's practically the same sort of performance that you get from a training run inside Azure Machine Learning. So it's really slow. So the best option for you is to actually have your model push samples into a queue, and that queue is then read by the explainer service, and the explainer service will then provide the explanation to whoever is interested. In the case of a customer, you want this to be fairly fast. So in that case, I would actually suggest limit the amount of samples that you load into your explainer, and you will be good to go. If you're using this for debugging purposes or for long-term monitoring, you can use however many samples you want. And the explainer service is just a Python application that uses DELX, InterpretML, or some other library for AI explanation. And it will push the explanation back to the application, or, if you want, into a tracing system. So what I mean by a tracing system in this case is a logging system such as the Elk Stack, Elasticsearch, and Kibana, or Azure Monitoring or Application Insights. You can use one of those as well. And that will give you important information to actually build a dashboard and give you a heads up when something's going wrong and somebody's getting an answer from your model that's not quite right. So this is sort of the architecture that I typically follow for explainable AI. Feel free, if you have a specific scenario in mind, to get in touch with me on Twitter. I can share my Twitter handle in the chat after this session, and we can certainly talk about it. It's a useful trick. Okay, but if you have this in production, then there's one more thing that you have to think about before you leave the desk. And that's actually, how am I going to present explanations to customers? If you decide that it's important to explain a model decision to a customer, for example, in the case of a mortgage or a loan, then you should keep these 6 things in mind. And that's a lot to take in, actually. So I will go over them one by one. And that's my final piece of information for you today. So my very first thing that I think about when I start using explanations and showing them to customers is make it selective. Only present the top 3 features to the person that's looking at the screen. Why? You could show them 40 if you want, but usually they look at the top 3 and then decide is this a useful explanation or not. So leave the rest out. Don't overload them. It doesn't help, actually. Then the second one is make it contrastive. So in the case of a decision about a loan or a mortgage, I would say show what would happen if the person was approved, what sort of input was expected then, and the actual situation if somebody was declined a loan or a mortgage. That's contrasting one prediction to another theoretical decision where it would be the other case in the case of classification, or a different outcome at least. And the reason why is that a person is then more capable of making a decision about what to do with the explanation. Should I maybe make sure that I have a fixed contract rather than a temporary one, for example? It becomes more actionable. The third one is focus on abnormal behavior. So if your model is doing the right thing, nobody's going to care all that much. Maybe sometimes, but not in 100% of the cases. So if you have weird behavior in your model, for example, you have an input sample that has values that are way outside of normal for your model, they are way off in terms of they are outliers, for example, those are cases that are interesting. So you can easily detect outliers if you want to, and then have an explanation generated for those outliers rather than the samples that are right spot on in the middle of your distribution of your data. Because the outliers, those are the most interesting to take a look at for your model, and if your model is doing the right thing. The fourth aspect that is important in terms of explaining AI to and explaining models to customers is think about social context. Choose the right wording for explaining behavior. So anybody who's used Grammarly, for example, what they do is they make a prediction to the user and they say, consider using this, or this. They're not saying you should use this. That's an important thing to keep in mind. And also, if you have a model that's unsure, we think that you will like this. That's what Spotify is doing. And in the case of an explanation, you could say, we think these are the top 3 reasons why your loan was declined. Things like that. So the 5th one, tell the truth, is a really important thing. This might actually be in contrast to limiting your explanation, but it really isn't not. It's not. Telling the truth is, if you have an explanation for one sample and you have another sample that's very similar to the first one, it should produce the same explanation, another completely different one. If that's the case, if you get a completely different explanation for similar samples, then you've probably used the wrong explainer, and there's something going on that the explainer can't handle. There's no one explainer that works for every model. There are many explainers, actually, that you can use. And the final one in my list is respect prior beliefs. And this sounds really weird. So if somebody suspects something, for example, I've been declined this loan because I have another loan that I can barely afford to pay for, then they know that it's probably the loan amount that's going to be a problem. And if you can, in your explanation, you should be able to confirm that. And if that's certainly not the case, then it isn't the case, and that's it. But if you can, please respect what somebody is believing about their prediction. The problem here is that if you provide an unlikely explanation for something, somebody will have a hard time believing you if it wasn't already sort of in the back of their head. So that's important to keep in mind. So if you're interested in learning more, and I can imagine you would, please go to my GitHub account. Everything is on there. So I have the data, the model, all the notebooks that you can run on your own machine and try it out. And please have a go at this and let me know how you fare. And if you have any questions, feel free to contact me. I'm open for questions, actually. I'm happy to help everybody who's trying to do this for the first time.